Dear students, welcome to my YouTube channel PCM Academy, and today I will discuss about pair production. This is also an important phenomena which proves that radiation has particle nature. Okay, so we are actually discussing about the particle aspects of radiation, and today we will discuss another two important phenomena, that is pair production and pair annihilation. Before we have discussed about photoelectric effect, Compton effect, that these are also the phenomena which proves that the radiation has particle nature. Okay, so then we will discuss about next the wave aspects of radiation also later on, that will be starting with de Broglie wavelength. But let me conclude today the class by pair production and pair annihilation. Okay, and that is the conclusion of, actually according to our syllabus, this is the conclusion of particle aspects of radiation. Okay, so what is happening over here? Suppose we have an atomic nucleus. Suppose this is a nucleus. This is a heavy nucleus. Obviously, suppose this is a heavy nucleus. Okay, and incident radiation of photon is falling on this heavy nucleus. Then it will absorb the energy. If the energy is suppose h nu. Okay, and it will produce two particles, one is electron and another is positron. Okay, so this is the actual direction of incident photon. Then this will be obviously will be scattered at an angle theta. Okay, to conserve the momentum along y axis, because this positron and electron have almost same mass and they will obviously propagate with same speed, that is speed of almost same speed, and these are antiparticle of each other. Okay, only difference is there, the charge is different. Okay, and the spin angular momentum will also be different, but otherwise if you talk about their mass will be same. Okay, so similar two particles, just one is antiparticle to other, so obviously charge will be different and spin angular momentum will be different. Okay, and we have to prove here. So here what is happening over here? So if this is gamma photon, then from gamma photon we have two particles, that is one is E plus and another is E minus. Okay, so this is a phenomena that will obviously prove that there is particle nature of wave. If you talk about this radiation is particle nature. But the important questions that arise from here is that why this heavy nucleus is needed? What is the role of this heavy nucleus? So if you analyze the momentum conservation, then you can understand that why this along x axis, if you along y axis the momentum is conserved, that's why this angle will be same. But if you talk about the momentum conservation along x direction, then you can understand why this heavy nucleus is needed. First, if you talk about the energy conservation, then this is very easy to understand, because the speed is the same as the speed of light in vacuum. So this electron has the energy mc square, and this electron also have this positron also have the electron mc square. So total energy 2 mc square. So h nu will be equal to just 2 mc square, and this is according to energy conservation. According to energy conservation. Okay. But if you talk about the momentum conservation, then the interesting thing will be happening. So momentum will be nothing but h upon lambda. Okay, or you can see h nu upon c. So c is equal to nu lambda, you know. So we have lambda is equal to c by nu. Okay, so lambda is equal to c by nu. So we have what is our p. So momentum is h upon lambda. So if you talk about h upon lambda, then you can see, so h upon c by nu, so h nu by c. So if you want to write in terms of h nu by c, you can write, or you can write in terms of h upon lambda also. So initial momentum along x axis is nothing but h nu by c, and the final momentum is nothing but the component along x axis, for this also p cos theta and for this also p cos theta. So it will be 2p cos theta. It will be 2p cos theta. Now if you write p as mv, then it will be just, and if you multiply this c here, so we will have h nu equal to 2 into p means mv, okay, into c into cos theta. into cos theta. Now you write it in this way. If you want to write in terms of mc square, then you can write it in this way also, that 2 into mc square into v by c. We can write in this way. So we have taken one c here, so we have multiplied with one c here, and it will be equal to cos theta. Now if you carefully observe this equation, you can see that this v by c is obviously less than 1, because c is speed of light in vacuum, and cos theta is obviously is less than 1. So if cos theta is also less than 1 and v by c is also less than 1, then h nu will be also less than 2 mc square, and that should not be happened, because you know from the energy conservation h nu is equal to 2 mc square. So here you can see this h nu is equal to 2 mc square, but here according to momentum conservation you can see that h nu is less than 2 mc square. That should not happen. So what is happening over here? Actually, why the momentum is less than h nu? Because this is because of the fact that when the photon is incident on this heavy nucleus, this heavy nucleus absorbs some momentum. So if the heavy nucleus absorbs some momentum p dash, then we have to add some term over here. Okay, so it will be h nu, and rest of the momentum is 2p cos theta plus the momentum absorbed by the heavy nucleus, that is obviously plus p dash. So if you add one term p dash here, then here will be just p dash c. So this term is less here. So our h nu is equal to actually with 2 mc square, as this is less than 2 mc square. So if you add something with this p dash c, that will compensate the term, the momentum that is absorbed here. Okay, so to remove this discrepancy, you can see if you add this momentum absorbed by this heavy nucleus, then the discrepancy will be removed. Okay, so that's why the heavy nucleus is needed. If there is no heavy nucleus, there is no absorbing momentum, then this phenomena, that is from gamma photon, electron and positron cannot be created, okay, or cannot be produced. Okay, so this is something about pair production, and the most important questions about pair production is that why pair production cannot happen in absence of heavy nucleus, and this is the explanation that I have told you. But for pair annihilation, this kinds of thing, no need of this kinds of thing, because that can happen in free space also. Okay, so there will be the thing will be different. But what will happen there in pair annihilation? If you talk about electron and positron, so when electron and positron collide each other, so they will produce two gamma photon. So in pair annihilation, what will be happening? If you talk about pair annihilation, so here in this case, if you talk about electron and a positron, okay, so they will annihilate to produce actually two gamma photon, and this is because of the fact that here electron and positron, the initial momentum of this electron and positron is 0. So if initial momentum is 0, if initial momentum is equal to 0, then final momentum should be 0, should have to 0. Then final momentum should also be 0, should be 0. Final momentum should be 0. So in that case, this will only possible if these two particles will move to similar particle will move opposite to each other. So that can only happen if there is two particles. So if these two gamma photon move opposite to each other with same speed, then you can understand that the net momentum will be 0. So the net momentum, the initial net momentum, as the initial net momentum is 0, so the final net momentum should be 0, and that will only happen if these two particles move opposite to each other with same speed, to similar particle opposite to each other with same speed. So this momentum and this momentum, when you add, this will be cancelled out, so the final momentum will also be 0, and that is the explanation that why in pair annihilation two gamma photon is produced. Okay, so this is all about the pair production and pair annihilation. You need to know just this phenomena according to our syllabus. So our particle aspects of radiation is concluded here, but from the next class we will start the new topic, that is the wave aspects of radiation. Okay, and that will be started from the de Broglie.